Hey, what's up, everybody? We're back again, once again, with our good friend Aaron Lease. What's up, Aaron? Back in the Chi-Town. So Aaron is over in Chicago, and he is going to. We're going to talk a little bit more about graphics. So this is part 3 of the graphics series. If you've missed part 2, be sure to go check it out. It's Juce tutorial 55. Can't believe we're over 50 tutorials in now. Yeah, not bad, huh? Half a century of Juce tutorials. Yeah. So how's it going, Aaron?
Pretty good. How you doing?
I'm great. So let's talk about graphics. So last tutorial that we spoke, we were talking just about ways to display graphics on a screen, and we had a float array where we were taking in the values of what was happening with the audio, and then we were relaying that over to the graphics side on the editor side, and we were just pulling those values in order to display the graphics. So, but that's not the best practice, is it, Aaron?
No, I mean, this is another way to say that is last time we did a video, Josh caught me with some old code. We were looking at it and it was like, oh, wait a minute, that's not the right way to do this anymore.
Yeah.
So we were looking at it's fine. It can be done that way for prototyping and whatever. But there was a thing we talked about in the last video, which was a definite improvement, which is has to do with lock-free programming, which is if we've got data in the sort of application layer, we're pushing it up into the UI layer. There's a bunch of rules around that, and you want to make sure you're not locking. They usually use different threads, so you want to make sure you're not locking the threads. Definitely don't want to lock the audio thread from the UI, so you need to pass data without locking and without using arrays and things where you can either have the threads locking up or trying to access the same data at the same time. So we're going to look at a solution for that, and broadly speaking, the solutions for that fall under what we call lock-free programming. And we're going to look at just the simplest possible type of lock-free programming. Right.
Great.
And I think you also did a video not too long ago on ring buffers, so this also kind of piggybacks on that, because this style of implementation for lock-free queues involves a very simple ring buffer.
That's great. Yeah. And just to reiterate on what Aaron was saying about reasons why this might not be a good idea. So in the audio buffer, it's a high priority buffer, which means you always have to keep it free as possible for passing in audio information. And what can happen is that when you're writing data, such as the audio value, into an array, and then at the same time you're trying to read that value out into the array that's where you're trying to display your graphics, that's when you get a lock, because it's trying to read that value and write that value at the same time. And then you get kind of a pause where it's saying, hold on, I don't know what I need to be doing here, reading or writing. And you get a pause, and what that could cause is discontinuities in your audio stream, and we don't want that. So that's the reason why we're going with this philosophy here of lock-free queues. So great. So shall we share your screen? And
yeah, do it over here. How do we do that?
So down at the bottom in the middle, there's the share button.
There. Share desktop. Oh, there we go.
Great.
All right. So this is maybe you can help me with this too, since you just did that ring buffer video. We'll do a sort of very short conceptually how the ring buffer works, and then look at the code. Does that sound okay to you?
Yeah, it sounds great.
Cool. So before this, I just did the Google image search of ring buffers, and you get all these futuristic. So what looks good? This one looks pretty good. Yeah. So here, Josh, you can help me with this, but the concept with a ring buffer is that there's a finite number of samples, and when you get to the end, you go back to the beginning.
Yes.
So a nice way to represent this, graphically, is as this cool little ring here, right? Mm-hmm. Within the ring buffer, there's always a point that you're writing, which goes around the ring, and a point that you're reading, which goes around the ring. And the idea is you never have to lock this thing, because whenever the reader comes along and says, okay, I'm going to read from the ring buffer, it only reads up until the right pointer.
That's right.
And then it stops. So you have to have a mechanism basically where you say, hey, the write pointer is at position 5 and the read pointer is at position 2, and I want whatever new data I can get. Well, that's going to be the difference between 2 and 5. So there's going to be like 3 samples in there you can get, and then you got to stop and say, okay, I've got all the new stuff I can get, and back off, right?
Yep.
This is smarter than doing it with the buffers where you would lock up the whole buffer. It's also smarter than doing it with, there is a way to do this where you don't lock a buffer, but you just read the whole thing, but then you get bad data. Because if it happens to be right in the middle of writing to position 4, then you get these like blown up numbers that turn into not a number and everything else and really screw up your programming.
Yeah.
So you need to keep your data clear, which means you never get to the right pointer. You just get the stuff that's in between, right?
Yep.
Sometimes this whole scheme is called first in, first out, or at least it's related. There's buffers where you kind of feed it new data, and that's the data that you get out. So the first thing that you put in is the first thing that's going to be gotten out, usually by a different thread.
Yep.
So that's the kind of world we're going to dive into. Do you have other thoughts on ring buffers at all?
No, I think that was a great explanation. So some people call this, just for short, a FIFO buffer, first in, first out buffer. And that's, if you hear the term FIFO, that's what they're referring to.
Yep. Okay, now give me one quick second just so we're on the same page as to the code we're looking at. This is the overdrive processor and the overdrive UI. We looked at this last time, so anyone who just did video 55 or whatever it was. And this one, yeah, so I'm going to show you this overdrive UI again, just so we're refreshed on what we're looking at. And then we're dealing with two things, the audio processor and the UI, different threads, of course. And then within the audio processor, the current system is it writes some data to a buffer, and then it reads it out over here on the UI thread. We're going to just change that buffer to be a ring buffer, and we're going to change the reading as well. We're going to change both of those to be a simple lock-free queue.
Great.
So let me pull this up. Now, I've already written it, so I've already written a lock-free queue, a very simple one. So we're going to talk through this, and then we're going to implement this class in the overdrive portion of it. So here, overdrive. Our overdrive plug, put it over here on audio. Have something to look at. So this. Turn that down so we don't actually have to hear it, but this is what we're dealing with, right?
Yep.
This graph, which is showing the audio going by really quickly. So it's like an oscilloscope, which is what we call it in the code here. So this little bit of the UI is controlled. Overdrive UI is this amp oscilloscope, right? Oscilloscope. So it's the amplifier or oscilloscope. Just my own shorthand. The right here. So here's what we were doing. We were getting an array of floats via get history, which pulls from the audio processor, and history is itself an array. That's what we need to change out. Right?
Yep. That's it.
Here, she wants to see what's happening.
Oh, hey.
Okay.
Dogs are welcome guests in these tutorials. So.
I gotta get her a herd of sheep, Josh. I gotta get her a herd of sheep.
Okay.
Hey, out! Come on. I'll lock her out if we have to. Here's the lock-free queue. All right. So let's take a look at this class now. First thing to look at is abstract FIFO. We were just talking about FIFOs. This is a Juce class, right? So there's this abstract class in Juce for a first in, first out style ring buffer. And it has a certain number, it has a certain number of functions that you should familiarize yourself with, which are the important sorts of functions that you need to construct a lock-free queue. Now, they're not complicated, but we don't want to get too far in depth with what these are.
Okay.
But the point is that with a lock-free queue, you usually say, you tell it that you're about to write, And then you tell it when you're done writing. You tell it also when you're about to read and when you're done reading. These functions just handle moving those the read
Pointers?
and write markers, right? So that you're smart about. You say, okay, we're about to write. It's going to lock down a certain thing. You know, write pointer stays here, then it writes here, but it doesn't let you read. And then you say we're done reading, and it moves the pointer. That kind of thing. There's no locks involved, as the name of course would imply. So this is your abstract first in, first out. Let me just check something. Oh, yeah, no virtuals. I thought with the name abstract, maybe it was a
Abstract class.
well, I thought maybe it had some virtual functions that you were forced to override, but it doesn't look like that's the case. Yeah, so it's not actually an abstract class in that sense, but that's okay. Oh yeah, and I don't even use it as an abstract class. It's not inherited. So here is that lock-free FIFO.
Yeah.
And we're going to put that in here, and then we're going to use it. Right. For these things.
So if you could go back for one, back there.
Yeah. Right.
Yeah.
So I'm creating a lock-free queue to wrap this, where I'm just going to do a few custom things around it. Right. It's a light wrapper, but when we create the lock-free queue, we need to create the abstract FIFO. 512 here is the initial size that's being passed in. Capacity.
Yeah. And why 512 or why powers of 2 there?
Well, I mean, this is an old habit, right? There's a lot of things in C programming that end up being a little bit quicker if you make them powers of 2.
I see.
So I don't know if that's the case here necessarily, but 512 is a good starting point. Also, it tends to be the size, most audio buffers, right? When you're in Ableton or whatever else, less so nowadays, but it used to be that all the buffer sizes were powers of 2, right?
Yep.
So a lot of times your buffer size is 1024 or 512 or 256 or 64.
Yeah.
And that's changed, and now you can get, other sizes and whatever else. But that's a lot of them still are like this. So a lot of times, a lot of sound cards will default to a size of 512.
Yeah.
So it's a decent size for that reason. We're not going to be reading every single sample, or if we are, we probably would want a bigger FIFO, but we'll get to that.
Yeah.
And then some of this is just very simple wraps, like lock-free FIFO. If I'm going to change the size, right, which we'll see, then obviously I have to change the abstract FIFO size. So it's a simple, just re-implementing set total size pushes to set total size of my FIFO. But I also want to do a few other things, like clear my internal data here that I'm using.
Yeah.
Right.
And just to we never really talked about float vector operations in here, but just to kind of give a really brief description of what that is, think of that just as kind of a for loop where you're doing something to all of your values within your vector. In this case, you're in your FIFO. So you could use float vector operations just to like if you look at line 45, you can basically just clear your whole FIFO.
Oh, this is what you're talking about. Yeah.
Yeah.
Oh, yeah. So these are great. Quick detour, but Juce has this class with a whole bunch of float vector operations. These are optimized for different platforms, right? So this has to do with memory. A lot of it's memory management. So it's copying this block of data over to this block of data, or adding these two blocks of data together, things like that.
Yep.
The nice thing is the implementations of these are different on different, Mac, Windows, different operating systems, and they all have different, special classes that optimize at a very low level. So this vector operations class has a bunch of very, very fast ways to move data around.
Amazing.
Yeah, so we're going to use that down here too. Okay, so here's the sort of guts of it. Is that I'm going to take read froms and write tos and use my lock-free, my first in, first out, to grab a certain amount of data and put it somewhere else. Put it into this local float array.
Yep.
Right?
Yep.
And there's, number to read, number to write. So the the reason why we're wrapping this is somewhat to decouple how many samples are available currently in the FIFO with how many I need at the end of the day. So I have this internal array where I can grab from the FIFO, but I also keep the older data.
Okay.
So that I can pass back more data than is currently available. So we'll kind of see how that works in a second.
Okay.
Write to array. This one skips it. Yeah, this is the one that we want to use because it's the fastest. Okay. So there's cases where we need to keep the data around, but we're going to skip that for a moment and just look at this one. Read to and write from are, so write to is going to be called from the audio processor class. So as the audio processor is going along, you're doing something with the data. Now, maybe you're getting the RMS data, right? You're doing the root mean squared of the ongoing signal. Maybe you are you don't care about every single sample, so you're averaging and you're taking every 10 samples, averaging down to a point, right? We talked about that in the last video.
Yep.
Because you don't always want every single sample. That's just too much data coming at you too quickly. So whatever form this data is in, we have data in the audio processor class, which is being generated. That data is going to be passed off into this lock-free queue via write to, right? So this is where the ring buffer is going along. Every time the audio processor does something, it's going to stuff something into the ring buffer, right? Later on, then, we're going to have read from. Later on, the UI thread triggers, and it's going to read some of that data out of the ring buffer.
Yep.
Right? And then I have this one, write to array, which is the one that we're actually going to use, which simply says, give me as much as you can of the most recent data. Just write it, and it hands an array. So it says, I'm the UI, for example. I have this array, and I just want you to pull from the ring buffer and add it to the array, because then I'm managing the array over here.
Yeah.
Right? It stays on my thread.
Yeah.
Okay. So that's the long and the short of it. We have a ring buffer. We have some custom operations reading and writing to and from this ring buffer. And we've wrapped it so that we can do a few custom things on top of it and save a few calls to the FIFO. So this one, for example, you notice does the prepare to write for the FIFO, but then it also does, okay, I've finished writing on the FIFO. So just to make things simpler, make one call instead of several calls. I don't want to be doing this every single time. Okay.
So quick question. So write to array. So you're copying the data from the FIFO to an array. Is that correct?
On this one, yeah, it's putting it
down at the bottom, line 136.
This guy?
Yeah.
Well, let's take a look. Destination. So it's giving it a destination, right?
Yeah.
So this is going to be called from the UI thread. The UI thread is going to say, hey, I got this array over here in the UI, and I need you to fill it with whatever you can from the FIFO. Right?
Yep. So you got an array that's sitting in your UI, and you're pulling from the FIFO into that array.
Yeah.
Great.
Exactly.
Yeah.
Yeah, and it's doing a bunch of these read froms, which is over here.
Yep. Great.
Okay, let's take a look at that. I do this in the waveform generator, so we're going to use this as a template. Yeah, here's the same thing. Got the number that's ready inside of this thing, and then write it to my array.
Yep.
So here's my get data. I'm going to use this as a template. Don't need to do this. Overdrive UI. So briefly, when it comes in and paints in here, rather than this get history, we're going to do something like this. So I'm just putting this in as a placeholder right now.
Yeah.
Get data from lock-free queue.
Yeah.
New way. And then meanwhile, this whole thing, get history is going to go away. So let's just start by torpedoing that.
So at the moment, what we're doing is we're actually implementing this wrapper around the FIFO class into our plugin processor.
Yeah, so we've already got the wrapper, and we're just going to take it and put it into the UI and put it into the audio processor.
Yeah.
So I'm going to take a look here at what it does in the audio processor, which is where we're writing, and copy that over. I just copied over the read stuff as a template. So here, in this other class wave generator,
So you wrote this in 2011? Dang, man.
wave generator? Yeah, I probably did this one, yeah.
You've been doing this for a while.
Some of them get copied and pasted, and it's a lie. That's okay. Okay, so in the overdrive, we just got rid of our history. Instead of a history buffer, we're going to do some sort of lock-free queue.
Yep.
It's going to call it my lock-free queue.
Yep.
Current history offset. Not sure we need that, but let's hold on to it for the time being. So lock-free queue in the wave generator. This is a handy thing. Probably going to have to do a get the lock-free queue, just like get history. Okay, at some point we set the size of it, set total size, smart to do it relative to the size of the audio buffer. So that if we have a larger audio buffer, maybe we have a larger lock-free queue.
Yep.
That's not fair to play, so we'll copy that over in a minute. And then here's the writing. So in this case, this is a wave generator. Wave generator is just generating like a sine wave or a square wave, that kind of thing. In this case, stride is how many samples. So every 20 samples, it's going to add to the lock-free queue. It's going to write some amount of data. Right? So this is for the UI. I'm going to copy this, and then we're going to take a better look at it and change it. Like overdrive. For now, we'll just leave it at the default size, 512. But then in process block, here's where it was doing history, right? So it was writing to that history array, and it was writing how often? Yeah, every 20, same thing.
Yep.
Every 20 samples, it would add one to the history array.
Yep.
Okay, boom, that's gone. Lock-free queue for the UI. Current audio. Every 20 samples.
Yep.
Right, 20, number to write, number to offset, number to write, this thing, wave out, wave, get unchecked, right. So it's just writing straight to it. I like it. Yeah. Well, here, just to make it easy, let's do this. Is this averaging? Yeah. Pi is 20, we just average. So we're not going to bother with dithering or averaging. We're just going to take every 20th sample. So you can do, there's more complicated, you know, we could go through and average them or find the maximum or any of that kind of thing, but I'm not going to worry with it right now.
This is my opportunity to see how a real developer codes.
Oh,
I'm much slower than this.
Without that. Okay, what's write to take? A pointer to the data and the number of samples we want to write.
Yeah.
So if I was going to write the whole thing, we could just get a pointer to the buffer. Put in the whole thing.
Yep.
Since we're not doing that, we're going to go through and just grab every 20th one and write a single sample, and then write another single sample and write another single sample.
Yep.
It's not, you know, you incur a little bit of overhead that way, but it's not that big a deal. Sample high number of threads. Get sample channel 0, channel 1. Set start. Yeah. Okay. One important concept to highlight a little bit in here, current offset, so that we get evenly spaced samples. Say we're taking a sample every 20 samples we want to sample, but there's 512 in the buffer. 512 doesn't divide evenly by 20, right?
Sure.
So we would get 0 and then 20 and all the way up, and then we would get 500, and then those 12 samples would just not be accounted for. And we would start again at 0, 20, etc. This is going to give you a little bit of distortion in your wave. It's not going to look right. You will be able to see it if it's something like a sine wave, because it'll just kind of jump in a funny way. So the way that we counteract this is we note what our current offset is. So if you have 512, you go 0, 20, blah, 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 blah. You hit 500, and then you say, oh, we're 12 samples. We have 12 samples extra, right? So then the next sample it's going to look for is going to be 8 samples in. It's 20 minus 12, right? So the next buffer it gets, it's going to say, oh, now I start on sample number 8. So that's what this current history offset is all about. Right here. Okay? I think that made sense.
So he's doing that using Modulo in order to get it to wrap around like that. So for anybody that's just getting into this, do not be scared of using Modulo. That's it's the best thing ever.
It's true. It is the best thing ever. Offset start plus. Offset start plus. Okay. And we modify this slightly so that it grabs the starting offset, and then we know how many samples we're going to write, spaced out by 20. This should really just say stride. Change it. Stride times I. We're averaging the left channel and the right channel here. Channel 0, channel 1. I happen to know that it's always going to be a stereo signal, so I'm not worried about that. But you may need to tailor it. Pending. Stride number to the right, offset, lock-free Q, right, the sample. Okay. Oh. I don't know if we should be taking an address of something temporary, but I think it'll let me do it. Okay. It doesn't look like it's complaining, so this will be writing. Okay. Yeah, it failed, but it failed for other reasons. Okay, we no longer have this, so I'm going to get rid of it. We no longer have this get history instead. So now we're in the UI. Oh, no, we're not. Oh, yeah, we are. In the same file. Now we're in the UI, and instead of, here's our old code where we said get history, and it just handed us an array, which was copied quickly from over on the AP side. So instead, we're going to take this code, which we just pulled out on another example. We're going to go through it and modify it quickly. So pointer to my amplifier, get lock-free Q. Remember, we copied this, just an accessor method. Get number ready. Important concept here. If we can go back, if we talk a little more on a wrap-up about ring buffers, ways that ring buffers can get confused. If it stops writing, and in other words, the write position stops moving, read position can catch up, and then it says, how much new stuff do we have? Oh, 0. It just has to sit there. How much new stuff? 0. The other complicated thing is if the write position goes too quickly, it goes all the way around. Say your ring buffer is too small. It goes all the way around, and it writes a few more. Then you say, give me whatever's new, and it says, I've got 3 new ones. Well, actually, it's written all the way around, so you missed 512, and then you get 3. Then you get jumps in your data. It's still a preferable situation because there's no locking, there's nothing's blowing up, you're just getting bad data. So it's better than if we'd had the previous situation where we had arrays and we're using locks, so we were not using locks and potentially getting bad data. But
say that again. You say that again. You slowed down. You said previous what?
The previous situation where we have just a float array, or we have a float array with a lock or without a lock, and we're going to get bad data, which might crash everything. Right? It's a better situation in a ring buffer if we've gone the whole way around and not noticed it. But that means that your data might be wrong. You might lose some data and get just 3 when you should have got 512 plus 3. So we'll talk about that in a minute. That's like error handling type stuff. The reason I bring it up now is that get number ready is important, right? Get number ready is the function that's just telling us where's our write pointer, where's our read pointer, how many new samples do I have, or do I think I have, right?
Yep.
So the UI comes along and says, how many new samples do I have? If that number is greater than 0, which it should be, we're going to grab that new data and we're going to peg it to my local array, which lives over in the UI, right?
Yeah. So why copy it to an array? Why not just get?
Well, we have to store it somewhere, right?
Yep.
If I'm drawing this oscilloscope, I don't want to draw just the new data, because that might only be 3 samples. I want to draw the most recent. Well, here, this is what it says. Grab the most recent 500 approximately samples, right?
Yeah.
Or whatever our history size is. We don't have a history size listed. Yeah, let's just make it 512 for the moment.
Yeah.
Yeah, that's going to change. So say we're going to, view the most recent 512. I presumably have an array living on the UI where I can store 512 samples, and I'm getting it from the lock-free queue, whatever it tells me is the next available stuff, and I'm just keeping it in a local array.
Okay.
Now, it's not an array that's on the audio processor, so I don't have to worry about locking. It's only going to be accessed by one thread,
which
is the UI thread, right? So that's the big difference that we need to remember. Is previously we had an array on the audio processor, and we would say, hey, give me that whole array, and it would copy over whatever's in the array. But if it was being written to, or if we had to lock it, those were the problems. This is a local array that just lives on the UI, so it's fine.
Yeah.
Read from the lock-free queue. So in my amplifier, get the lock-free queue, and I'm going to use that write to array that we saw before, right?
Yeah.
And then I have to hand it an array. Now, I don't know if I have an array currently, so let's take a look. I do not. So that's what we still need to create that. So we're going to do that. So an array of floats, just called history. Right?
Yep.
Just for fun, history size. Okay, we're keeping 512 of them around. So history. Sure, allocated.
And what does that do? Just make sure that you have 512 values.
Yeah. Is there resize, right? Yeah. That size resize.
Oh yeah. So that reminds me. Remember that this is a Juce array, not a STD array or STD array.
It's a Juce array, which, as opposed to a STD array, can be resized.
Yeah, so just like the last video, I was looking, and when I saw ensure storage allocated, I thought, hold on a second, this array needs to know what its size is at compile time, but Juce arrays do not. So Juce arrays are more like a vector.
Like a vector, yeah. So local array for storing history data, right? History, just the most recent audio data.
Yeah.
So I ensure that a certain number is allocated. I resize it to that size. I clear it. I wouldn't actually have to do ensure allocated, but it's like a good thing to do.
Yeah. So resizing isn't the same as ensure allocated?
Ensure allocated. So ensure allocated just means that the space is available in memory for it.
Okay,
So
sure.
it says, like, here's this array, and because we know it's a vector and it might get bigger and smaller, we want to make sure that it might grow to be as big as whatever. So maybe I want to allocate all of this space, even though currently it's only this big. It'll be moving, so I want to have this bigger box for it to live in,
Yep.
so that it doesn't ever have to reallocate to a new place in memory, which takes, more time, more CPU time. So if you want to avoid that, which is often the case, you ensure that there's ample storage that's allocated, and then the array, which, as we discussed, is more like a vector, can grow and shrink without outgrowing the amount that is allocated for it.
Okay.
So in this case, it doesn't really matter because I'm ensuring there's a certain amount of space, and then I'm using all of that space, and we're not going to change the size. And we're going to do a position, which tells me my current position within where I'm writing the most recent data. Mm-hmm. So when I get data from the ring buffer in this, lock-free, safe way, I'm then going to put it in an array. But the array is going to live again on the UI where it's safe. Nothing else is going to access it at the same time.
Mm-hmm.
Okay. History position. This is like the local write position then for right here.
Mm-hmm.
For our local write position for that history array. So let's just walk through this again.
Yep.
Clean it up, make sure it's clear. Yeah, there we go. Okay, so we call, this is our audio processor, call the lock-free queue, find out how many new samples we have.
Yep.
We then take those new samples and write them to an array.
Mm-hmm.
This is where we hand it our history array, and I hand it the current position in the array, which is what this asks for. Handing it the hand it the array, hand it the position in the array, and the lock-free queue takes those 3 new samples or whatever, and it writes it to that array.
Yep.
Even smart enough to wrap around. If it's right at the end of the array, it wraps around to the beginning.
Mm-hmm.
I then move the write position on the array on the UI thread, right? Number added over history.
Mm-hmm.
This should be, we'll just do this. Okay. This is probably where position value. Yeah, this is where it's doing this, which we don't have to do right there. I'm going to do it down there instead. Okay, so this, we're going to trim some stuff out. This is all we needed from that code to replace our get history, right? Instead, we get the lock-free queue, get the number that's ready in the lock-free queue, we add it to the local array,
Yep.
and then we move the write position on the local array.
Yep.
Once that's done, we're ready to build the path. The path is what we're going to actually display in the UI.
Mm-hmm.
So we go through the history. Remember, the history is pulled from the lock-free queue. That's every 20 samples. So we're getting every 20th sample, putting it on this local history, and we're going to build a path based on those samples.
Yep.
Just for fun, we also find the minimum and maximum. Well, just the maximum. Find and use that to change the color of the thing, right? And then scale to fit and draw. Now, this is going to be anticlimactic because if this works, let's see if it's building yet. When this works, the goal is to have it look exactly what I showed you at the beginning of this whole process.
Yeah.
Right? We haven't changed the way it looks. That was all covered in the previous video. All we've changed is how it's getting that data.
Yeah.
So if we wanted to, in the old one, we could have sat here for 5 minutes and we would have seen, here's the waveform, and every once in a while there'd be a bad piece of data.
Yeah.
Like a spike would happen.
I see.
And that will no longer happen.
I see.
Right?
Mm-hmm.
Let's see if we got that.
The anticipation's building.
We'll take a look. I think that should be it. But we changed everything on the audio processor side, changed everything on the UI side. We now have a different mechanism for getting that data from the audio processor to the UI, which was the goal here. And if it's clean and displaying properly, then we've done everything. There we go.
Okay.
Built. So let's run Ableton. Oh, and we got some bad data. Oh, no, I know what this is. This is an icon that changed. This happens sometimes if I load the old plugin and it loads a block of data. I don't quite understand this myself, but it basically means that I can't load the auto-saved thing in Ableton. We'll have to create a new one. This. Aha. There's a problem. We got arithmetic error. Take a look. History. Size is 0. That's our problem. Oh. Is clear remove whatever's in there? Yes.
Yeah.
That's not setting it to 0. That's removing the samples.
Yeah. This kind of helps segue into one of our future tutorials that we're going to do on debugging. So that's coming
right.
soon.
We're going to do that, aren't we?
Yeah, coming soon to a theater near you. Debugging in Juce, C++.
I have a feeling there's a quicker way to do that, but we're just going to do it this way. I'm going to set everything to 0 to begin with, because if there's gunk in there, then you can get bad data that could crash everything. See if it'll let me see if it auto-saved that. I think it did. Cool, VST, overdrive. It's happy.
All good so far.
Yeah, there you go.
There it is.
Oh, it looks a little slower.
Uh-huh.
I think this has to do with the number of samples that I have writing in there, so I probably need to make my array a little bit bigger, or change the stride so it's not every 20 samples, but every 10 samples. So that's good, because it actually looks a little different than it did before.
Yeah.
As you can see, like I said, kind of slowed down, so we're going to speed that up. But the data is coming through.
Fantastic.
Fantastic. Totally anticlimactic, right?
No. We don't have any more discontinuities, so we're all good.
We're all good. All right, so that's the quick lock-free queue thing.
Yeah.
And I think we basically covered it, but
yeah,
just looking at this, again, the one problem that you want to be careful with is that you are not writing so many times and reading so few times that you write everything and overflow, spill into it again. Because what can happen is this write pointer, here you see the read pointers going through, and there's whatever this is, like 10 samples till it gets to the write pointer. If the write pointer had gotten the whole way around and then added a few, then you would
only have 3 values to write.
It would say you only have 3, but you would have missed an entire ring.
Yeah.
So that's the one. That's really the one thing you have to look out for in this style of lock-free queue. And the other thing that we should mention, which I think we mentioned briefly at the beginning of this is one type of lock-free queue, and it's the very simplest kind, where you have a single producer, one thread writing to it, and a single consumer, one thread reading from it. You can also have situations where you have a single producer, but lots of threads come in and read, or where you have more than one thread which can write and more than one thread which can read. When that happens, it gets much more complicated very quickly. Luckily, we don't need that for what we're doing. We have just the audio processor and the UI, and we can just have this kind of simple scheme.
Nice. I prefer simplicity.
Right?
That's right. Great stuff. Yeah, thanks for taking the time to show us that.
Yeah, I hope that was quick enough and clear enough.
Yeah, I think it is, and probably in the future I'll probably do one just on the FIFO class on its own, just going into a little bit more detail. So, yeah, that sounds great. Would it be safe? Would it be safe to say that anytime that you're doing any type of ring buffer that in audio, I mean, for most situations like this, that a FIFO would be the best approach? With that,
Yeah, I mean, FIFO is just a wrapper for a ring buffer. It's basically what takes this buffer and automatically makes it a lock-free ring buffer.
yeah,
So it's a great starting point.
yeah,
I feel like there's a way to do this even simpler. If you want to reuse it the way I am in a bunch of different classes, it kind of helps to do that small a wrapper that just handles a few different things.
yeah,
But if you're only doing it in one place too, you just take the FIFO and you can use it pretty much as is, as a ring buffer for passing the data back and forth.
yeah. I see. Great stuff. Yeah, thanks again, Aaron. And like I said, we're going to be doing another video at some point in the future where we're going to be talking about debugging and finding out what's wrong when things go wrong.
Yeah.
So
I think we could do a whole series on debugging, but we can pick out a few really choice topics.
Yeah.
How to quickly debug things.
Yeah, great stuff. Well, thanks again, Aaron. We'll end things here, and I will see you next time.
See you next time.